Alright, so to better explain Snell's law, I went ahead and I drew a diagram here. I'm expressing the wave two different ways here. I've got my ray diagram, and it's interacting with this surface. So let me change the color of that surface. Alright, there's my surface right there. Okay? So I've got this ray that comes in, strikes that surface, and then gets transmitted through that surface. Okay? So here's my plane waves coming in. So here's the plane waves coming in, and then at this instant it just strikes that surface. So because of that property of absorption and re-emission, that piece of light right there that just struck that surface is now going to travel at a slower speed. Okay? Which means that it's going to travel less distance in the same amount of time it takes for it to do one oscillation or to accomplish one wavelength. It's going to be less distance, so the wavelength is going to be smaller. Now let me explain that a little better. So as the wave hits that surface and slows down, it's still going to be a red light, or it's still going to be pink, or it's still going to be a microwave, or whatever it may be. And those properties, the color, the microwave, the gamma ray, whatever it is, and I'm looking over at my chart over there, whatever it is, it's still going to have that same property. Now that property, if you think about it as energy, has to be described by its frequency. It's the expression of the energy. That's that frequency. Okay? So it's not going to strike that glass and be visible light, and then as it's traveling through the glass, red. So the frequency has to stay the same. Okay? If it's going to strike that glass as red light, it's still going to be red light. If it's frequency. So that means if it's being damped as it's traveling through that medium, it's letting my camera catch up with this. Slowing down through it, as it slows down through that medium, its wavelength has to reduce. That C equals wavelength times frequency. C gets smaller, S stays constant, so wavelength is smaller. So the other way to think about it is because wavelength or frequency can't change, strikes that material, so it's going to take a shorter distance to accomplish that wavelength because it's going to travel slower. It's going to go, instead of going really, really fast, it's going slower. Okay? You hope you enjoyed my frequency sound. Okay? So these spaces in between these wavefronts have gotten smaller. And those spaces are wavelength. That's one wavelength, remember? Between wavefronts, that's a wavelength. As it strikes that material, you can see all the wavelengths just sort of piling up. Hence, boom, it bends. And it bends the light at that instant as it strikes that material. What I have over here is I have a diagram of what's going on. And I'm using a couple of definitions. Maybe I'll do this with my left hand. I'm actually kind of slightly ambidextrous, but not all that much. Strikes, and here's the ray that travels through here. Now I've got one wavefront that just barely interacts with that surface. So we're talking about this section of the wave. Okay? It strikes that surface, and then I have another that starts surface and comes out. Okay? So here's my ray. My wavefront, it has to be perpendicular to my ray. That's the definition of a ray. Same, my ray to be perpendicular to my wavefront. Cool? So that's my geometry. Now I'm going to wipe this down, and so I need a space to work in. Because I'm using water to do my dirty, dry it off so you can see the chalk. Okay? Cool? So what I got going on there is I have a relationship. And I have this piece of both triangles that are in common. Nowhere are my angles equal. And I'm mostly concerned about these two angles. Okay? This angle here and this angle here. Okay? I'm going to call that theta 1, theta 2. They're not equal to each other. They can't be. This size, or this piece and this piece are not the same size, but this piece and this piece are. They're not equal. Okay? So what I'm going to do is I'm going to say, well, this is a wavelength, and this is a wavelength. Okay? And those are not equal to each other, so I'm going to call this one wavelength 2. I'm going to sine of wavelength 1, or sine of theta 1, is equal to wavelength. And I'm going to say d sine of wavelength 2, or sine of theta 2, not wavelength 2, is equal to wavelength 2. Okay? Now this d and d is this piece. It's equal. And d is equal to each other. So just looking at the top one, I get the equation of d equals wavelength 1 sine of wavelength 1. Or sine of theta. Okay? Well, now I can set those equal to each other. So I end up with taking this logic and applying it to the sine, or to the second triangle. I get this relationship. I can set them equal to each other because we know that both of those d's are equal. And I get this relationship. I'm going to move this one over to here, okay? And I'm going to use this last bit of board over here to do the rest of it. So I have 1 sine theta 2 equals 2 sine theta. Okay. Now, the next thing I'm going to do is I'm going to say, well, that wavelength is a representation of how fast it's traveling. It's giving me the distance. It's a distance by the amount of time it takes to do that one wavelength. In a sense, it's period. Those periods are identical, so I can just multiply all the way across by t. And it's the same t because it's the same frequency, because it's the period frequency. And I end up getting v theta 2 equals v2 sine theta 1. Cool? Now the last two I'm just going to do because it needs to be done. We're talking about light. Light has one fundamental property. It has its speed, 3 times 10 to the 8 meters per second. It's talking incredibly fast relative to other things. So treat it as how much faster is it, or how much slower is it in that material. So I'm going to divide everything by c. Okay? And this right here, the velocity divided by the speed of light, is what's called the index of refraction. Okay? Every piece of material, even air itself, has its, own index of refraction. So that is going to be n1 sine theta 2 equals n2 sine theta 1. Okay, and I'm going to erase that one section so it can stand by itself. Okay? So n1 sine theta 2 equals n2 sine theta 1, where n is the index of refraction. It's the ratio of the velocities. The velocity in a vacuum, 3 times 10 to the 8 meters per second, divided by the apparent velocity through that material. Okay? Index of refraction multiplied by the sine theta is equal to n2 sine theta 1. Got it? That is Snell's law.